Women continue to be disproportionately affected by HIV around the world, especially in sub-Saharan Africa, where 3 in 4 new HIV infections are among young girls. But what can be done in these communities where access to once-a-day pill preventatives is non-existent? Welcome to another episode of the Uncommon Engineer podcast. I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering. The Uncommon Engineer discusses how Georgia Tech engineers make a difference in our world, in our daily lives, and in ways you might not expect. Our guest today is Dr. Phil Santangelo. He's a professor in the Coulter Department of Biomedical Engineering between Georgia Tech and Emory. His research is focused on treating diseases like HIV through RNA-based therapies, and he's getting close to delivering an HIV preventative for women. Welcome to the program, Phil.
Thank you for having me.
So I'd really like to just jump straight into your work around prevention of transmission of viruses. It's so incredibly exciting and so incredibly, so much potential. And I know that you use RNA. And so before we kind of get into that, I think most of our listeners have had high school biology and they learn a little bit about DNA and RNA. And can you kind of start at that level, remind everyone about RNA, and then maybe segue into how you're using it to prevent transmission of viruses?
Sure, absolutely. RNA stands for ribonucleic acids. RNA are your cell is full, all of your cells are full of RNA molecules, and they have, for the longest time, they did not think they had a lot of function, that they would act as an intermediary between DNA and protein. But over time, we found that not only do they are they translated into proteins, but they have other functions also. And so folks started thinking about, could we use them as therapeutics? Could we use them? And there's been a history now of probably 20 years or so where folks have been thinking about how to use RNA as a therapeutic. But it was really, I would say, our journey into using RNA really started from a detection point of view. I was interested in viruses and viral pathogenesis, and we started creating probes to detect viral nucleic acids, specifically viral RNA. And, and the viewers should realize that most of the significant viruses that cause disease in humans are caused by viruses that have RNA as their genome, as their gut, so to speak.
Let me see if I have this right, because I think most people do think of, part of our nature is encoded in DNA, and you have potentially or actually identified segments of RNA that you, like you said, you are fabricating your own RNA. And so the idea is you have found the segments in the RNA that we might modify or change or alter so that down the line, as RNA does its work, the changes in RNA that you facilitated result in ultimately kind of our own immune system providing new therapies to combat various diseases. Your work is beginning to receive a lot of attention because of the potential really revolutionary new therapies or a kind of supercharged immune system based on RNA. What I'm hoping you could do is talk a little bit at a high level, but around preventing HIV or significantly lessening HIV
Sure.
transmission or other virus transmission. Could you talk about some of those experiments and the
Sure.
results and
Sure.
where you are?
And so we started delivering RNA actually into the female reproductive tract. And we did some pilot experiments with a colleague of mine at University of Louisiana Lafayette in a macaque model, and we saw some pretty astounding data regarding our ability to express antibodies against HIV in that space. And so we went to the Bill and Melinda Gates Foundation and said, hey, you guys are very interested in preventing HIV. And even though PrEP is extremely useful, and there are some limitations to PrEP. You have to take a pill usually every day, and even though there's some long-acting PrEP coming, I think, in the near future, but there are also some side effects to PrEP too. And so we thought, is there something really simple that we could do, inexpensive, and that could last a long time, that could shield women and possibly men too from HIV? And so when we talked with them, they were specifically more interested in preventing HIV in women in particular. And we embarked on a number of experiments, both in a number of different animal models, to examine our ability to produce antibodies against HIV in the female reproductive tract. And we've been actually quite successful in that area so far. We have so we've done a number of experiments where we have a very simple formulation. It would be something that a woman could easily give to herself whenever she wanted. It's really very straightforward, and we have some evidence that it can last up to 3 months, actually, which is pretty exciting, and I think possibly longer after a single dose. And so this was incredibly exciting for us because we are thinking now that not only using this for HIV, but for other applications. And we recently received an NIH grant, or I should say it's about to show up, on another application of using RNA in the female reproductive tract. And so there has been a lot of incredible drugs, a lot of really interesting work out there. But actually in the last 20 or 30 years, there really hasn't been as much research as one might imagine. And so I thought this is a tremendous opportunity for us. I mean, anything that we do that could affect the health of half the population of the Earth is pretty exciting, if you ask me. I mean, if I finish my career and we've helped to prevent HIV, maybe and other pathogens and other issues in women in a way that allows them to apply it when they want to, and it's safe. And I mean, it's a little pie in the sky, I'll admit, but at the same time, if that's the goal and we could achieve, make gains towards that goal, even in my career, I'm going to sleep really well when I'm finished.
There's the flip side of, turning the immune system, supercharging the immune system through methods. One of the things that we keep hearing about, particularly from the defense community, is kind of the opposite. Are we worried that an adversary is going to develop something that turns the immune system against people? And as a weapon of war, can some of the tools that that you and others are working on, how do we prevent the unbelievably positive advances that y'all are going to make, but for those adversaries who may want to use that same technology to turn us against us? What are your thoughts on that? And how can we prevent it? How do we prevent it? What do we do as a society to make sure that doesn't happen?
This is a very big topic of conversation right now. I've been involved in discussions with the CDC in the last month, discussions with DITRA and DARPA about some of these issues, and there are ongoing conversations occurring regarding this particular issue and what safeguards need to be in place, both in the lab, even at Georgia Tech. I mean, we do have CUI controlled and classified information requirements actually on this grant. And so how do we deal with information? How are we ethically releasing information? And so I do think that this is an ongoing conversation, and it's certainly not, it's evolving, but it's certainly a conversation that's occurring. I think one of the ways to prevent the evil parts from happening is to continue communication among all of us. So as a community, as a scientific community, really making sure that we're communicating about what we're doing and how we're doing, about the ethics of what we're doing and how we're doing it, about communicating with the public about the experiments that we're doing, what the goals of the experiments are, what we're trying to achieve in those experiments. And at the same time, really communicating again among even folks in the lab. I mean, really trying to build a community of ethical behavior.
Your ability to kind of supercharge, through messenger RNA, the immune system is, I think even folks who just have had a little bit of biology kind of get that. And that's amazing. I think I have so many questions. First one kind of, my guess is when you make this RNA, again, I'm an electrical engineer.
Sure.
Kind of imagine creating, a bunch of, a small sample that you could do in the lab. And in order to turn it into a therapy, I think I recognize that you need to replicate this by thousands, hundreds of thousands, millions, billions, as you develop a therapy to really, truly attack something. And so that kind of scaling process of taking something, in order to turn something into a therapy, making your special sauce and then scaling it up.
Sure.
Can you talk a little bit about that? Because where I'm actually really headed towards is you're a biomedical engineer. You're not a physician. You know a lot of basic biology and basic science, but at the end of the day, I think you're an engineer, and I'm
Sure.
really curious about how being an engineer. So I asked about how to scale, but I'm also kind of asking. I bet you there's an engineering piece to that, other than just the basic science.
So there are a number of engineering aspects to this problem. I mean, everything from literally engineering of the molecules that we're making, the mRNA itself, but you're certainly right that production and scale up is something that we're going to have to confront. I mean, we've already done this. Interestingly enough, even in the lab, when we started, we were making pretty small quantities. I mean, microgram quantities. And then we had to take, at a certain point, we had to actually stop and say, let's assess our current process. How can we change this? Because first of all, it was too expensive. And so we started looking at changing sources for some of the chemicals that we use. And so we actually started making relationships with some of the actual primary manufacturers of some of the enzymes that we use in particular. And so by making those relationships, we were able to go right to the source. We were able to cut costs significantly, but then we had to optimize the process. And so I had one student and one postdoc who basically spent a month, I think, or two in the lab doing nothing. And I mean in the lab. I think they went home sometimes, but optimizing this process. And so it took a bit of work to do that. And since then, we've been continuing to optimize, and scale up is a part of. Now, whenever we say optimize some aspect of RNA production, we then immediately go into scale-up mode. But scale-up mode for us are hundreds of mgs now. So we went from micrograms to hundreds of mgs, actually. And we even have companies who want us to make RNA for them. And so we've scaled into hundreds of megs pretty easily. I think we can get to grams without a ton of work just at Georgia Tech, but you're certainly right. Once we get, I think, beyond grams, this will have to transition either to one of the RNA pharmaceutical companies, have them pick it up, or, to be honest, there's some interest in our own lab about starting a company to produce RNA, because we've had interest from a number of companies for us to produce RNA for them, which was a little surprising at first. But I think, we're very open about what we do and how we do it. In addition to that, the way we characterize our product is a little different than some of the manufacturers out there. And so I think that's an opportunity. But just the same, I think eventually we're either going to start our own company to move this forward, or we'll transition it to a partner.
What got you to where it is you are now in terms of being an engineer and wanting to do the things that you do?
Sure. So I have a crazy path, and I always tell students that my path to where I am now is circuitous. It goes across the country. Various parts of the world. And so I would never have predicted that I am doing what I'm doing right now. But there is I would say there is a unifying theme, and that is I like solving problems. I mean, that is what I like to do. Hard problems, difficult problems, crazy problems. I mean, that's what I jump into. And so I actually started as an aerospace engineer. And so I was trained as an aerospace and then mechanical, and I worked in thermal fluids for a long time, and I worked in optics, and I loved airplanes growing up. I mean, loved them, rockets, space program, and so that was what I enjoyed tremendously. But over time, I was more and more interested in the science behind fluid mechanics, and I really became an applied physicist, I would say, more than anything else. And then I decided at a certain point, because of I was working in industry, and that industry was starting to have a lot of problems. And so I thought, where should I focus my attention now? Where are there really important problems that I could focus my attention on? And I thought biology was the next place to do that. And I'll admit, even when I worked in combustion for a while. I was at Sandia National Labs as a postdoc, and I'll never forget this, but Paul Miles, who was a researcher there, he may still be there, said to me, there's limits to what we can do in this space. Go find a problem where you don't think there are limits and see where you can explore. And I thought that was, at the time, I thought, what's he talking about? And so, but then at a certain point in my career, I thought, hey, biology, that's the place where I think there's limitless things to do and problems to solve.
So, Phil, one of the questions we always ask on the Uncommon Engineer is what makes you an uncommon engineer?
A lot of things. But I think my background, one, that I have two things. My educational background is pretty varied, and my training is pretty varied. At the same time, I would say also I've worked in a lot of different places. Started out in academia. I worked in government for a little while. I was a postdoc at Sandia National Labs. I worked in industry for a little while, then came back to the academic world. But I think that diversity of experience, of thought, of interactions makes me, I think, reasonably uncommon, even though I think that's becoming more common, which I think is a good thing.
Can't thank you enough for coming today and talking with us. You know, the work that you're doing is just really remarkable, and hopeful. There's a lot of patients out there when they hear those kinds of things that make them very, very, very hopeful for the work, and really grateful for the work you're doing, and for choosing Georgia Tech to do all that work. So thanks for coming, and thanks for everything you're doing for the campus and for at least half the population of the globe. Thanks,
Sure.
Bill.
I appreciate it. Thank you.